just wait a minute. How was the bagel? Was it everything?
Yeah, it is definitely, it's a proper meal. Yeah, in San Francisco, it's like just bread with something.
Yeah.
Yeah, I think it was
Good.
worth it.
So maybe we should go ahead and get started. Alright, excellent. Alright, we are very happy to have Aishik Ghosh here today. Aishik is a postdoc at Berkeley, working with Ben Nachman on neural networks and applications of physics. He's going to tell us about some cool physics he's been working on for 5 years, is that right?
That's right.
On applications of this, the Higgs. Alright, so without further ado, take it away.
Thanks for the introduction. And thanks for inviting me here and for actually coming. I know today isn't the best day to come and listen to a talk, but I promise I'll distract you from everything else for the next 1 hour. So I'm going to talk to you about Higgs physics with something called Neural Simulation-Based Inference. Maybe it's some of you have heard about it before. It might be new to several of you. Just a flavor for what's to come. This will be about statistical inference, so there will be some technical slides, but I made sure that there's also an intuitive explanation. So if you've decided that it's too late in the day and I don't want to follow the math, that's perfectly fine. You'll still get an intuitive understanding for what we're doing. And I'm going to cover work that has been covered over 3 papers. So this is a phenomenology study I did back in 2019. Of really showing the proof of concept of why we need to do this kind of high-dimensional statistical inference. And then we actually implemented it, we figured out how to implement this kind of a method in a full experiment, quantifying all of the systematic uncertainties and so on. That really took, you can see, a gigantic amount of time. And then we applied it to actual round 2 LHC data, and we published a paper with new limits on, well, a new measurement of the Higgs width. So I'm very excited to talk about all of this. Taking a step back, from the beginning of humanity as we know it, we've been very interested in answering some of the fundamental questions about, on the one hand, what are these elements that make up everything that we see, but also, how sure are we about the conclusions that we're drawing from the data we have in front of us. And so today, the people who try to answer the first questions, we often call them theorists, and the people who try to answer the second questions are experimentalists. But the kind of questions we're interested in nowadays are a bit more specific. You might be curious what 85% of all the matter in the universe is made up of. We know it's dark matter, we really don't understand how it works or the physics behind it. We're also curious why there's so much more matter than antimatter in the universe. There are some theories that might explain it. We want to confirm these, and possibly the most exciting stuff, at least from collider physics, is trying to find new forces or new particles specifically. That would be very exciting and spur all kinds of new research. So all the matter that we do see and understand can be described by the standard model of particle physics. So here you have the quarks. These ones make up things like the protons and neutrons you're used to seeing. Here we have the electron and its cousins, they're called the leptons. On the right, we have the force carriers like the photon and several other bosons that allow you to communicate, the other particles to communicate with each other. But possibly the most interesting one, at least for me, is this Higgs boson right in the middle. It's with the interaction, the other particles interacting with the Higgs field, that they are able to gain their mass. And so we also think that if there is some as yet undiscovered massive particle out there, maybe just beyond the reach of our colliders, it might still be getting its mass through the same mechanism, the Higgs mechanism, which means it'll be secretly interacting with this Higgs, with the Higgs, right? So by studying the Higgs boson, we can indirectly probe for the existence of all kinds of new physics that might be outside our direct reach. And which is why a lot of us study this for a lot of our lives. And And to generate heavier particles is more and more difficult, so you need to inject more and more energy into your system. We do that by taking a couple of protons at the LHC and accelerating them at the speed of light almost, and then we smash them together. Right? That creates a whole firework of particles. We want to see what's exactly going on, so we have these gigantic detectors that we design. We have millions and millions of sensors in them. Each of them provides some independent information. So really, if you think about our raw data, it is at the order, the dimensionality is at the order of 100 million dimensions, right? So our image, if you think of it as an image, is 100 million dimensional. And if you want to do probability density based analysis, we would have to somehow build a 100 million dimensional histogram, which nobody knows how to do. We don't even try to do that. So instead, we use very sophisticated algorithms. Hundreds of physicists work on this to try to go from this 100 million dimensional space down to one number, right? With reconstruction, event selection, all kinds of things. And then we have thousands and thousands of such collision events. Each of them is summarized into one number. And then with that one-dimensional data, you can build your histograms, and then you can start to analyze the data. So maybe a theory prediction, say, if your background-only model has this falling distribution, and if there's a signal, then it'll sit on top of the background like this. And then you have your data. Of course, the data is not labeled, but you can compare the data to your simulations to try to measure some parameters. Let's say the most typical one is a signal strength measurement, which enhances the overall normalization of the signal, right? So maybe mu is equal to 1 is your standard model prediction, and then you're trying to constrain the value of mu. So you're asking the question, what value of mu is most consistent with the data that I see? Right? This is the kind of analysis they're very used to doing at the LHC for a long time.
Just a naive question.
Yeah.
So you say it's 100 million dimensional because there are 100 million sensors. Is there no time series for these sensors? Is it really just one snapshot?
At the moment, no, but we do have timing detectors coming in that give some kind of that kind of information, but it would still be very different from like time series data the way you think about it in, I guess, LIGO or something. Yeah. Yeah, that's an interesting question. Okay. So why is it that, so you might be wondering, we have this gigantic high dimensional data, why is it that we can get away with summarizing it into one number? Turns out there is this lemma known as the Nyman-Pearson lemma that tells us that depending on what hypotheses you want to compare, you can actually bring everything down to one number. That particular thing is the likelihood ratio. So let's say D is your data, then what you want is the likelihood. Numerically, it's equivalent to computing the probability of getting this data given some hypothesis value of mu, and you can compare that to some other reference value of mu. Right, and this contains all the information to do optimal hypothesis tests. Yeah.
So maybe this is like the one political question. Is this like the most powerful in the, this is like a frequentist framework. We're not doing anything Bayesian.
That is right. Yeah. First of all, it's frequentist, and then this only works for simple hypothesis tests.
Okay.
So as soon as you have, we're talking about parameter estimation, which is a composite test, and then the Nyman-Pearson lemma is not guaranteed to be the best thing you can do, but till now nobody's been thinking about doing something better than that.
Okay, so so if I start asking tricky questions about what's like the natural distribution on like some parameter space of priors I could have, this is
no, these are interesting things. Of course, we are not doing Bayesian statistics here, so we don't have priors. So you can consider priors on the nuisance parameters. We don't call them priors, we call them constraints, but they really come in exactly like a prior. But for the parameter of interest, we don't want to say this theory has a higher prior than that theory.
Right. Because who's to say?
Right. So yeah, that's why, I mean, this is the whole thing of why we want to stick with frequentist. But okay, this is a matter of taste. Particle physics, since we have a lot of these IID type data, somehow we tend to like frequentist statistics. Cool. Then, how do you build this in practice? Turns out you can train a neural network classifier to separate your signal samples from your background, and you can somehow use that to build this likelihood ratio. And even before machine learning, basically if you could build a strong discriminant separating signal and background, that would help you converge to this guy up here. But yeah, if you have a classifier, then it's very straightforward. So the classifier knows nothing about the parameter you want to measure, right? It's just looking at signal and background. And then you can construct any likelihood ratio you want. Let's say P of xi is an event, individual event, for some value of mu over, let's say some mu equals 0 reference. You can, since you know the dependence of signal and background on the parameter of interest, you can really write it down as this function, and then it comes out to be some function of the output of the classifier. So s over 1 minus s. These all terms are constant, so they're easy. So really, regardless of which value of mu you want to test, all the information you need is inside the output of the classifier. So this is how it guarantees that one number can actually contain all the information you need to build these kind of likelihood ratios, which is very convenient. And yeah, this is why you don't need to re-optimize the analysis for every value of the hypothesis you want to test. And we've been getting away with this for quite some time. And these are the core of frequentist hypothesis tests. We compare likelihoods for different hypotheses given the data, which, as I said, numerically is equal to computing the probability of the data to the hypothesis. And the physics that I care about, that I told you, is the Higgs width. So remember, I said if you have as yet undiscovered massive particles out there, they could very likely be interacting with the Higgs. And what happens if that is the case is that the Higgs width will get enhanced. What is the width? In quantum mechanics, it tells us that all particles have some distribution of the mass. They don't just have one fixed mass. And they are centered around the pole mass of the particle. So when we say Higgs is 125, we're really talking about this point over here. The distribution has a width, and that is called the width of the particle. And the more interactions the particle has, the wider the width becomes. And so if the Higgs has interactions with these new particles that we don't know about, then its width will be larger than the standard model predicted value. Right? So by measuring the width, if we see that it's larger, we have indirectly convinced ourselves that, okay, there is some particle to be found if we built a larger collider or something. Awesome. And in fact, this is one of the central measurements, if not the central measurement that we talk about all the time when we are discussing not just the future of LHC, but really building a muon collider or a circular collider and so on. Is we often talk in terms of which one will give us better constraint on the Higgs width. Right, so this is an important measurement now and in the future, but there's a challenge. So I've been talking to you about these kind of problems where the parameter of interest linearly enhances the overall cross-section of the signal. But when you have quantum interference, let's say between these two diagrams over here, this is a Higgs diagram, this is a background diagram, but both have the same initial states, 2 gluons to the same final states, the Zs will go to 2 leptons each. Then all the processes that can take you from the initial states to the final states, all of them can and do occur at the same time, they interfere. And that produces nonlinear effects. If you see over here, the blue distribution is the background only case, if there was no Higgs. And the pink is background plus signal. And the first thing you notice is it's not an enhancement on the number of events, but really a deficit. And it's not just a reduction in overall normalization, it really changes the full shapes of the distributions in very nonlinear ways. And then this whole premise that we're working with breaks down. And I claim that in these complicated cases, you can't just summarize everything into one observable and be done with your analysis. So let me give you first an intuitive reasoning for why that might be the case. Imagine that your actual data space is two-dimensional, which is nice to visualize. And your first theory predicts a lot of concentration of events here, but the second one predicts data there. Then you can compress this to a 1D projection. I mean, you could just read off the x-axis and you'll still get nice separation between the two theories, and you're happy with your summary. But if I have a third hypothesis here and a fourth one there, the 1D projection can't really tell them apart, but the full view, high-dimensional view of the data can easily separate that, right? So this is the intuition for why we want to go to high dimensions if we could. And if this doesn't convince you, let's look at actual simulated samples for this analysis. So this is the distribution of the mass of the 4 leptons in a Higgs to 4 leptons analysis. This is usually the most important observable to look at. And we're looking at full simulation, so signal, background, and interference, everything together for different values of the parameter that we want to measure. So mu equals 0 is the background hypothesis, and then 1 is standard model, 4 is lots of enhanced Higgs, and so on. So it's new physics, 4 and 5. And so the challenge I like to give is, can you spot the green curve? So if you look very carefully, it's right underneath the blue one, which means the background, mu equals 0, looks the same as mu equals 4. This is quite mind-boggling to at least sparring physicists who are used to seeing these kind of plots, because this is very different physics. Blue and green are very, very different physics. But they look the same in the most important observable. But that doesn't mean the physics is the same. If you look at another observable, the dijet delta eta, then you start to see that the blue and the green can be separated. And the point I'm trying to make here is it really depends. Which two hypotheses you're comparing will tell you which observable is the most useful one to look at, right? So I'm not saying that these two are now enough to do everything. You really need to create a new observable for each value of mu you want to test.
That mu is scaling up this process from the previous slide, from the standard model value?
Yeah, but in a funny way, which let me show you. So what it's doing is, let's say x is an event. So the probability of seeing a particular event with some form of momenta has two contributions: the matrix element from the signal and from the background. But because these are complex numbers, and when you add and square them, you also get this interference term. And when you don't have interference, this is basically negligible, and then you can just add them up like normal, and then you see the old scenario of the signal just going up and down. But here, there is this non-linearity, so the total number of events really goes as, there's a square root of a mu term here, and then, yeah, it's not really, so we think of it still as scaling the signal, but really the whole distribution is being scaled in a funny way. And then this nice little trick we were using before doesn't work anymore, because this whole thing assumes that this thing is 0. So when we add this back, there's no way to get all the likelihood ratios just from the output of that one classifier. And in fact, this is not just for one particular Higgs width analysis. This challenge is true for a very large number of analyses. In fact, a lot of the analyses we want to do now going forward are more complicated than also in the effective field theory framework. And here you have lots of different parameters with many different nonlinear dependencies. So the question is, can we again find a way of doing statistical analysis of the LHC that is near optimal, so that we can really make the best of our data?
This is really to do with quantum inference. I didn't quite understand. Why do the nonlinear effects do quantum inference and not just do nonlinearities?
Yeah. So let's say the probability of seeing a particular event with the sum 4 vectors of the final state particles, right? So this is really, it comes from the Feynman diagram for the signal, Feynman diagram for the background, and then this interference term, right? So this is the matrix element for, this one is the matrix element for the signal diagram and the background diagram, but the full, when you want to compute the full amplitude, you need to, yeah. And then, so if you are defining this parameter as something that scales S linearly, you are forced to scale this as square root of mu. And since you're writing this down, earlier you were saying mu times S, basically the contribution from signal, and no mu times B, you can't just, you don't know how to plug in the third term here. Okay, awesome. I really like questions, so please feel free to
Sorry, a dumb question. So can't you modify the numerator there by adding the square root of neutral? Because it's also something.
Yeah, but you can't get it to be in a way that you can try. So you will never find a way to just write it in terms of this guy.
Okay.
So you need to do something else. This guy, this classifier that doesn't know about the parameter of interest, will never have all the information. Okay. Right, so we want to find a more general solution. and since I'm saying, okay, you can look at multiple variables, the obvious idea is, why don't we just do the analysis with 100 variables or something? But that's hard to do. Think about density estimation, which we do with histograms typically. If you had to populate a 1D histogram just with 6 bins, how many events would you need to try to get an idea for the shape it's approximating? Maybe 50, 100 is good to get a first idea for the shape, right? But now try to do the same thing, 6 bins on the x-axis, 6 bins on the y-axis, in a 2D histogram. How many simulated samples do you need to populate this full grid? You have 6 square bins, it's already a lot more samples. And then if you try to populate a 50-dimensional histogram with 6 to the power 50 bins, you're basically, we'll never make it. We'll never have enough samples to populate this. And remember, my actual dimensionality of the data set is 100 million, right? So I'm not even close to that yet. So this is the curse of dimensionality. And yes, how are we going to deal with it? We know by now, I mean, it's been more than 10 years that we know neural networks can actually scale to high dimensions. So the idea is to come back to these formulae and somehow adjust them to get the likelihood ratio. So this is the same as before. We want to get that, the likelihood ratio. And now, instead of training signal versus background, we're going to train one hypothesis versus another hypothesis. All right, so the classifier is now learning the probability that this event comes from the hypothesis mu1 or whether it comes from mu1 or some reference, right? And then it becomes very straightforward. If you want the likelihood ratio, you just take S over 1 minus S, and you're done. This is, of course, this classifier only works for one value of mu. You need to train another one for another value of mu, and so on. In fact, it can be done with one network if you condition it, but I'll show you more about that later. But essentially, this can be done, and then suddenly you have an optimized analysis for every value of mu, which is really valuable. And the bonus is that, look, we're getting these likelihood ratios per event. They're xi dependent, right? So we don't need to put them in histograms anymore. So we don't lose information by putting multiple events in the same histogram. So we're maximizing that information as well. I want to point out that this core idea was actually, it came up in NYU. I think Kyle Cranmer and Gilles Luc were here when they came up with this fundamental idea of using classifiers to get this kind of likelihood ratio. And we've now taken it to the full application. Cool. So this is the idea of neural simulation-based inference. Traditionally, we would take this high-dimensional data, summarize it into a histogram, give that to a statistical fit software. We also tell the software, of course, which hypothesis it is we want to test. And the fit works for a while and then gives us some likelihood of the mu given our data. I want to drop this summary completely, take the high-dimensional data, give it instead to a neural network. Again, I tell it which hypothesis it is I want to test. And I want the network to give me this likelihood ratio between some value of mu and the reference. And these networks can be trained on simulations and applied on data, which is why it's called simulation-based inference.
So actually, I had a question on just the last slide. A slightly naive. So on the far right center equation that signals, so first x is like some vector of observables that we're interested in, and these crucially could have like interference amongst them, which is why we need to account for this in the technique. And this is like the probability of seeing those particular observables quantum mechanically given, like mu is like some shorthand for one hypothesis.
Yeah.
So I buy that we can do simulations and train a neural network. Is there a reason in principle not to just compute it ab initio, or is the idea is that it's simply too hard?
No, it's a very important question. If we could do it from scratch, then we wouldn't need neural networks, and that would be great. There are a few challenges with that. We don't know how to calculate quantum field theory at infinite order, so there are some uncertainties, but you could actually handle that without machine learning. The part you can't is the detector effects. So you can do these ab initio calculations all the way to the matrix element. Already after hadronization, we don't have an analytical formula for it. And then once you make it go through the detector, we have no known.
There's not like a model for how the detector effects. No. But does this simulation account for detector effects?
Yes.
How do we don't have a model for them, but we have code that simulates it.
Absolutely. In fact, this is how this whole idea used to be called, or it used to be called likelihood-free inference, which means like we can't write down a likelihood, but we can simulate. So the simulator is much, yeah, it's doing very complicated things which is not tractable.
Okay, maybe the much more sharpened version of my confusion is how we have not enough theory to like analytically talk about the detector effects,
Yeah.
but enough theory to write down code that implements a
Yeah,
description
yeah,
of that.
yeah. I'm not a person who
Fair.
writes that code, but as far as I understand, it's wait, what was the word? Yeah, I mean, you can think of like emergent phenomena, right? Like you only know how to write like individually how a particle interacts with some material, and like something happens, but you don't know. What the
It's
long-
simply too hard to do by hand, so we simulate it.
Yeah,
Okay, fair enough.
yeah. And there are also ideas on how to use the simulator and get back a probability, which you need to. So this is called. Why is everything escaping? It's called probabilistic programming, where you can actually get some of this back. You need to make the detector simulation differentiable. There's work going on in that direction as well.
I mean, just to make sure I'm understanding, like, to your question, you are able to calculate this, it's just computationally expensive, right? So you make you do a bunch of simulations, you get a simulated data set,
Yeah.
and then you train the neural network to act as a kind of interpolation function,
Correct.
so that you can now apply it to lots and lots of real data.
Absolutely.
So it's
Absolutely.
not that you can't compute it, it's just slow.
This is much cheaper at inference
This is
time because we
easier,
want
yeah.
to do inference time like order of 10 to the some large number of times. Or something
We
like this.
can, I mean, that's a bonus, the fact that the inference is super fast, but like, if we could do it slowly but exactly, that would be perfectly fine. We just can't, like, yeah.
It's just very hard.
Yeah.
Okay.
And this is a common problem in like many fields where like you have a forward simulator, but you can't run it backwards. Cool. All right. So yeah, so neural networks nonetheless can like kind of invert the simulator and get back this likelihood. So that's what we're gonna do. And so I did a phenomenology study on like how would this affect our Higgs width analysis. So I'm going to first show you some expected sensitivity for a beyond standard model value of mu at 4. And so this is a negative log likelihood curve. What you need to understand is all of these methods on the data set that we test, they all minimize at the true value by construction. So what you care about is the width of this curve. Narrower it is, the sharper your measurement. The more quickly it rises up, the more confidently it rejects the wrong values of the parameter. And in the colors, you can see the different kinds of ways you could have done the histogram analysis, the traditional method. Some are better than the others, but really the method that blows all the others out of the water is this proposed method using neural networks. And I want to point out that this red one already uses machine learning. So the point is not just to use some machine learning, but it's really to use it for high dimensional statistical inference, and that's how you get this improvement in power. The rate information here, if you're wondering what this means, it means whether you want to include the overall cross-section into the analysis or not. There are some systematic uncertainties in that, so we tested it in both cases. I'm just showing you the one without rate, but in all cases, the black one does better. Here is actually at the standard model point, which is what you care about, assuming this is the true value in nature. And again, you can see that the neural inference method just significantly outperforms everything else. Now, this kind of improvement is quite unbelievable, especially for such an important analysis. People tend to these kind of Higgs analyses have a huge group of physicists who work and fine-tune everything. So usually you work really hard to get a 5% improvement or a 10% improvement. So it's reasonable to be skeptical at this level while it's still a pheno study. But the point is to
Why
be...
is the machine learning approach worse than the simple histogram?
Yeah, that's a good point. So it's because the machine learning approach is still summarizing everything into one observable. So it can only be optimal for one value of mu. So it will happen to be good somewhere in the space, but not here. It's definitely not optimized for mu equals 14. Yeah, and that's the point. Like at some point, one will be better than the other end.
But neither is yours, right? You have to tune it for every mu, like every mu1.
Mine, this method is parameterized. So it is, you train it once and it automatically learns how to optimize the whole thing for the full method. Yeah, so if you did this, you would, you could train like 100 different networks for each different value, and then you would have to use a separate observable for each fit, which has its own challenges, but in principle could be done. And I think in effective field theory, if you know studies, often people will use different observables at different points of the parameter space, precisely for this reason. Okay, so we want to bring it into the Alice experiment now, this idea. It is very challenging because there are several unanswered questions. First of all is around robustness. You're giving up this likelihood that you get from histograms and replacing it with a neural network that kind of estimates the likelihood. Are you really going to trust it? So robustness is a big problem. Systematic uncertainties, all of this study that I showed didn't include systematics. How are we going to include that? And then something called the Nyman construction, which is a way to enforce coverage of the method. It's a very frequentist way of doing it. Cool, so we're going to see how we answer these questions because we did solve all of this over the last 5 years. And we put out this note not too long ago, just last week, on the full implementation of this idea, including uncertainties and so on. And then this week we put out the full measurement of the Higgs width with this new method, and it supersedes the previous result on the same data. Atlas doesn't usually publish two results on the same data, but when you get this kind of improvement, it's worth publishing twice. All right. So how did we solve everything? Here's the big picture, and then we'll go into the technical details. The big picture is, instead of one network, now we have a set of neural networks that solve individual pieces of the problem. That makes it more robust. But we also have additional neural networks, each for one source of systematic uncertainty, so one nuisance parameter. And each of them adjusts the final likelihood ratio to correctly quantify the impact of their respective systematic uncertainties. Okay, and each of these boxes that I've shown is not one network, but really an ensemble of hundreds to 1,000 networks, and that allows us to quantify the uncertainty coming from the neural networks themselves. Now, they're not trained on infinite data; they are not perfectly trained anyway, so you need to somehow account for those uncertainties, and we do that as well. This required training at the order of tens of thousands of neural networks, which thankfully we could do on HPCs, and then the fits we can do with JAX, which takes advantage of the fact that all of these likelihoods are now differentiable. So now I'm going to go into the technical details of what actually happened. So first of all, we designed what is called a search-oriented, what we call a search-oriented mixture model. So instead of just training one network to learn the whole likelihood, we're going to break up the problem. So let's say this is the probability of this event xi given some hypothesis mu. It can always be broken down into contributions coming from the different physics processes, the Higgs process, the background process, any other process. So the J here is really summing over all the different processes going from the initial state to the final state. All right, and so I also want to give a concrete example. So I'm going to show you a simplified version of the full analysis with only 3 processes: the signal process, the background process, and the full process, signal, background plus interference. The actual analysis has many more processes, but we're going to ignore that for now. Cool, so what do these terms mean? First of all, F, J mu. These come directly from the theory model you've chosen to interpret the data. So for example, if you're measuring, doing your analysis in terms of some signal strength mu, then this is something you know just from the theory. So you don't need to estimate this, you know it going in. Then comes news. These are the event rates which you get from your simulations. So again, they're estimated just from measuring, counting the total events you expect from simulations. Nothing fancy to do there. So the only challenging one is to calculate the probability of this event for given some physics process J. And to do that, we're going to use a trick. We're going to divide on both sides by a reference hypothesis, which in this example is just going to be the signal process. Okay, this choice is completely up to you because I'll show you later that it doesn't matter, it cancels out. But numerically, certain choices are smarter to do. I'll talk more about that later. But yeah, once you divide on both sides, you don't have probabilities but probability ratios, and these we can estimate using classifiers, as I mentioned earlier, right? So in fact, we're going to use ensemble of classifiers to really get a robust estimate. Cool. Intuitively, what we're doing is, let's say you're comparing some hypothesis mu versus some reference. You know that the contributions to these are from the same physics processes. Whatever mu you choose is the same physics processes. So you can break up the problem into getting the likelihood ratio between the green and the gray and the blue and the gray and so on, and then put them back together using this formula over here. And the very nice thing then is that the dependence on the parameter of interest is known analytically. And so the network doesn't need to know anything about the mu. So we just take, let's say here it would be 3 networks and combine them using this formula, and we then get the full dependence on mu exactly. A quick caveat is that like exactly the formulation of f mu will depend on the basis functions you've used to simulate the sample. There are many choices you can make. Alright. So I talked to you about how to design it in a robust way, but anyway, now you have to look at the networks and make sure that they're giving you the likelihoods that you really wanted. So how do you validate these high dimensional likelihoods? One way to do it is with reweighting. You can think of like taking a network and turning it into a generative node. So let's say you have these 2 high dimensional distributions. I'm showing it to you in 1D, but let's say you want to reweight the blue to look like the green. What would you do? You would take events in this lower region and give them higher weights, maybe greater than 1, so it covers this gap. And here you give them weights less than 1 and it shrinks down and starts to look like the green one. What exactly are these weights? Well, they are the likelihood ratios between these 2 distributions, which I claim I have already estimated with my classifiers. So if I just plug in these values from my classifiers, I should see that the blue starts to look exactly like the green. And if I look in this high dimensional space and I find any corner where the reweighted sample doesn't look like the green one, then I've convinced myself that in that part of the phase space, the networks are not getting the likelihood ratios correctly. Does that make sense? Okay. And then so I'm going to show you, again, the reweighting is happening in high dimension. I can only look at it in 1 dimension. So I'm showing you a few 1-dimension plots. First is the mass of the 4 leptons, one of the most important variables. So the source is going to be reweighted to look like the target, and the reweighted sample is in orange. And we see that the green and the orange agree quite nicely. This was used to train the network. Then we use, for a closure, we look at some high level variable that was never used. And again, we see that the green and the orange match pretty well. Pretty well, of course, in our subjective, you'll see how we convince ourselves it's good enough. But before that, now you might wonder, okay, you've chosen to look at a few of these 1-dimensional projections and everything looks nice. What if there's some part of the phase space in a weird projection where actually you see the discrepancies and you just forgot to look there? So to make sure we actually capture the high-dimensional problem, you can do a classifier test, which means you train an independent classifier, another machine learning model, that tries to separate the target from the reweighted sample, right? And if it achieves any level of separation, it means that it has found some phase space where the 2 are not the same statistically, right? And if it finds an AUC of 0.5, which means that it's completely failed. That means that these 2 distributions are statistically equivalent. And we do optimize our analysis until we get an AUC of 0.5. There are several plots. I'm only showing you 2 here because I want to show you some other diagnostics. This is called the calibration curve. So remember I said, each ensemble gives me this kind of a likelihood ratio. So I'm showing you an example here, mu equals 3 versus reference. And then you can bin the whole data in this output of the network or the ensemble. And then in each bin, you can compute empirically how many events come from this and how many come from this. So you can really compute this term just from within each bin, and that is what we've written on the y-axis. And if the network has estimated this correctly, then the y-axis and the x-axis will completely agree. So you'll see a y equals x diagonal line, which is what we see. This is not trivial to get. If you just train a classifier and you try to do this, you'll see a weird S-shaped curve. So yeah, we had to really optimize the networks to get this nice diagonal line. Then you want to run the whole analysis on test data sets where you know the true value of mu, and you test it at different points. So you, let's say, whatever, 0.1, 0.9, whatever, 4, and so on. And in each time you see what your maximum likelihood estimate is going to be. And you want it to, again, follow this diagonal line. So whenever the true value is 1, you want the maximum likelihood estimate to also be 1. And so we do see that, so that's good. And yeah, so, was it a question? Okay. So these are the kind of diagnostics. I want to show you also an interpretability plot that we can do now that we couldn't do before. Because we have likelihoods per event, you can plot them as a function of any variable that you want. So here we're looking at, we're asking the question, which part of the phase space is more compatible with the mu equals 0 hypothesis versus mu equals 1 hypothesis. So we can plot that as a function of the mass of the 4 leptons, and we see that, okay, in this region is more compatible with 1, in this region is more compatible with 0.5. And that kind of makes sense because we know that in 0.5, this part of the phase space is suppressed because of heavy quantum interference, and so this favors mu equals 1 instead. And also what's nice to see is that no matter which two hypotheses we test, the tails are often, are always insensitive, so they are exactly at 0, which is good because this is where our simulations start to break down. We don't have enough statistics here, so if it were picking up something here, then it might have picked up mismodeling of our simulators, and luckily it's not sensitive to these kind of fluctuations. Cool. Now moving on to systematic uncertainties, how do we plug in systematics?
Sorry, can I just ask a question about the previous part? So
Yes.
you do this reweighting, right? But you have an extremely high dimensional parameter space that's sparsely sampled. So some places of this space are empty. So do you put in, because I mean, as you said, right, you use 6 to the 50s, so such high dimensional, you don't have as many samples. So you put some smoothness on these probability functions, or?
No, yeah, this is a very important question. So we are right now not going to 50 variable. We have, I think, 16 to 20 depending on how you count. But yes, it's still very high dimensional. The nice thing about neural networks is it already has a smoothness function. So by neural networks are self-regularized, and then you can regularize them more. But yeah, the whole magic of neural networks is that they somehow don't pick up fluctuations. They smooth through fluctuations, which is a challenge when you want them to pick up the fluctuation for some reason. Yeah. But nonetheless, we test this, right? We make sure that like it shouldn't pick up the fluctuations.
So would it be harder then if you had some high concentration?
Yeah.
In this,
So this is a challenge we have in places where, let's say, the mass of a particle is very peaked. If mass is obviously at one point, and if the width is small, it's peaked, and neural networks will often miss that. So then you need to like add some additional loss function that makes it focus on these kind of sharp distributions. We have this problem for generative models. Yeah, absolutely. Yeah, I don't have a plot for that, but we have another paper where we have to add in loss functions to make it pick up these sharp peaks. Cool. So systematics, we have two kinds of systematics. Experimental ones where, let's say, you've calibrated things wrong and there's a overall shift in your distributions, and the even more challenging ones are theory uncertainties, where, let's say, you just don't know how to compute QFT to to maximum precision in every way, so you have some kind of strange uncertainty for that. And in our experiments, they're all represented the same way. You have some nominal prediction, and then you have a systematic up and down variation. And so you have to make do with that. And neural networks require more than 3 points to interpolate. So this is one of the biggest challenges for this method, that we never knew how to make it work for our systematics. But in traditional analysis, what we would do is, in each bin of a histogram, you have these 3 points, and then you would fit one of the known analytical functions that we know usually interpolates these things quite well. So we're just going to take that idea and extend it to the per event level, where instead of doing the interpolation per bin, you just do the whole interpolation per event. And that gives us the full probability model, including these nuisance parameters alpha. And so this looks like a big equation, but really you've already seen this before. This is the whole statistics stat-only contribution. And so there are a few new terms. These guys, as you can see, have no xi dependence, which means they're not per event terms. So they can be estimated the same way as with traditional analyses, which is from the simulated predictions and the interpolation method that I just talked about. The only new term here is the small g, which is actually also another likelihood ratio. Is between an event coming from green versus the event coming from red, which again we know how to estimate using neural network ensembles, right? So we have every term in this equation and we can get the whole likelihood ratio for every event. Then we can construct a test statistic where this term is what you saw in the previous slide, the per event likelihood ratio. You have to multiply it for all the events, of course, and then you have an overall rate term, overall cross section, and you have some prior, a constraint term on your nuisance parameters. And then you have, that's it, that's your test statistic. And this looks very much similar to what you would do in a traditional analysis, except for this LRF term at the bottom. The denominators are unusual. But what turns out is the next step you traditionally do is you do profiling. So you do a constraint fit and an unconstrained fit. So you let this one, the mu is fixed, like you fit only this guy, the alpha, or you fit both of them, and you take the ratio of them, and then this LRF completely drops out. And you get back the traditional profile log likelihood ratio, which doesn't have this reference term. And this is what I was talking about earlier, that the choice of reference doesn't matter, because when you finally get do the profiling, it drops off, as long as you don't plug in any new dependence into it. And then you get the usual profile likelihood curves that we're used to seeing in particle physics. The red here is the neural network method, and the green is the histogram method. And you have both the stat only and stat plus systematic full profile. By the way, this for those of you who are used to seeing parabolic shapes, the reason this is not parabolic is it has to do with the quantum interference. It has nothing to do with the method. So you see it both for the histogram analysis and the NSBI. In fact, the NSBI recovers some of the parabolic shape because it's able to use more information. And so yeah, this is what I was talking about. The reference choice of the reference is arbitrary conceptually, but numerically it makes sense to choose something that has a support over the full range of your analysis, because it's coming in the denominator. So if the p ref is 0 anywhere, you're in trouble. So you need to make sure. So we define it to be the combination of all signal Feynman diagrams, so that it has some non-zero value anywhere you look in the analysis. All right, there's one other uncertainty, which is the neural networks. We don't believe in them. Believe that they're going to get perfect likelihood, so we need to quantify that uncertainty. The uncertainty is on the fact that it's not trained on infinite data, right? So if you have a population, your simulated sample is some subset of this infinite population, and what you can do is then sample from this with replacement. You take an event, then you put it back, and you randomly sample another event, and these give you bootstrap samples. And this is a traditional statistical method to assess the variance on the mean. So you can use the same idea. So you have your ensembles. Each of the ensembles is trained on a bootstrapped version of your training data set. And yeah, that can be used to get this kind of a distribution. But the trick is, we're actually using the entire ensemble to estimate a likelihood ratio, right? So to simulate multiple possible ensembles, you need to bootstrap the networks themselves. So there are two levels of bootstrapping that go on. So this is the kind of spread you'll see. So each color is now an individual event, and we've evaluated all the networks on them. And you can see that the distribution is the distribution of the outputs. So for some events, all of them give the same output, so it's a narrow distribution. And for some, there's some uncertainty. This means that the networks have not seen these kind of events frequently enough, so there's some variation. And yeah, that allows us to quantify this kind of uncertainty, and that is propagated into the final likelihood. You need to make sure that all the correlations are in place, and we do that with something called the spurious signal method, which is also an ML version of something that we've done before. Okay, then comes the Nyman construction. To do this, you need to generate pseudo experiments. So you need to pretend that like you've done the experiment thousands of times and see on average how the performance of your analysis is. How do you do that? Like, well, if you could use simulations, but we've all the simulation we have, we've already used to do these studies. So usually we do random fluctuations on our simulated samples. So in a traditional analysis, you would take a bin, and these are boson distributed, right? These are counting experiments. So you can plug in the measurement. So let's say it's, I don't know, it expects 0.1 events. You plug that in, and you get a new fluctuated version of what you would get here. In a per event analysis, you can't just look at a histogram, you can look at the full high dimensional data set. So instead, you can do Poisson fluctuations on the weight of the event. Each event has some weight, and then you can sample a Poisson number. These numbers that are coming out are integers, right? It's 0, 1, 2, 3. So you can treat them as unweighted samples, and then do your thing. One thing to keep in mind is, of course, you can have negative weighted events. So the way quantum field theory calculations are computed, the higher order terms often contribute negative weighted events. So you can't calculate the Poisson of a negative. So you need to start with a positive weighted sample and reweight it to the right parameter point in the parameter of interest and the nuisance parameter. And since the network always produces positive weights, an event that originally has a positive weight remains positive. And then you can do the trick that I talked about in the previous slide. Okay, if that was too technical, I mean, here is the basic concept. So we will take a data set with the true value of mu equals something, and then we will generate lots and lots and lots of pseudo experiments, do the whole analysis on each of these pseudo experiments, and see whether how the test statistic is distributed. So it's distributed like this. And that allows us to really define that this is our 1 sigma 68% confidence interval, this is a 95% confidence interval, because 95% of the time the true value lies within this range. And so this is a very frequentist way of ensuring that your analysis always has the right coverage. And you do this for mu equals 0, 1, and you do it for every value with mu. So each dot you see here has been done in this very expensive way, and this gives you the confidence belts. So yeah, this is your negative log likelihood curve, and where it intersects, this gray line tells you your 1 sigma and 2 sigma limits. Right, and these wavy shapes that you see, they're again due to the physics. We see the same for histogram analyses as well. And the nice thing we see is, again, in this quantum interference impacted region, NSBI really improves over the histogram method and allows us to set much, much better lower limits, or by rejecting basically the null hypothesis of mu equals 0. So that's very encouraging to see. But so now let's take a step back and understand why we're doing so much better than the traditional method. So first, we have in green the histogram method, and in red the NSBI method. The NSBI method, as I said, is optimized over the full range of mu, so it's parameterized and it's unbinned. And let's understand how much of the gain is coming from parameterization and how much from unbinding. For that, we have to do an intermediate kind of analysis that you might not be able to do in reality, but we can do it for this toy test case. So here we design a new observable, each for the correct, we design the correct observable for each value of mu we're testing. So you can see here the green plus uses an appropriate observable here, so it outperforms the histogram-based analysis, even though this is also still using a histogram to do the fit. But of course, this same observable would not be sensitive somewhere else. And then what you can start to do is increase the number of bins, and then you go from the green to the yellow and all the way to the red. And if you were to actually go to infinite bins, these dots would start to approximate the sensitivity of NSBI. So the advantage comes primarily from parameterization and then from unbinding. And then the most exciting thing is, of course, all of this I showed you on simulated samples. We actually applied it on real data, and that's led to the second paper. So again, here NSBI versus the histogram analysis. There's a lot going on here, but basically, so expected is the average expected sensitivity you want to have. The observed is the actual sensitivity you have from after applying it on data. And so we see that both for the expected, we see a gain between NSBI and histogram, And then for the actual data also we see a big gain. We've always expected a higher gain at these low mu values because they are impacted by quantum interference. And it so happens that the observed data set gives us a better sensitivity than we expected, which is totally fine. It's like expected is an average and observed is an individual instance of a data set. And so we see an improvement for the histogram analysis, and we also see an improvement for the NSBI. And of course, the gain is larger because the maximum sensitivity gain comes from here. So we had predicted that we would get a huge improvement in lower limits. We actually get a huge improvement in lower limits.
So you say expect this, you're saying that you did the simulation many times and you draw out that curve and then observe as you take the actual.
Yeah.
Okay. Then why should we expect that to be that much difference then?
Yeah. So like the expected, we do it on something called an Asimov data set, but you can really think of it as being equivalent to if we had, we had like generated tens of thousands of pseudo experiments, seen what the sensitivity would be, and just take the median of that, right? So the median is somewhere in the middle. So there's a 50% chance that any actual observed data set will get better than that. So yeah, we happen to get better than that. But again, like it's not a feature of the method because you can see already with the histogram analysis, also it's moving in the same direction. The observed is better than the expected.
But to that point, you could have gotten worse too, right?
Yep.
And that would have also been consistent. Okay.
Yep.
You can presumably put some error bars on how much you expect the real sample to fluctuate.
That's a good point. Yeah, that's a good idea. Yeah, we should put these things. I don't think we've ever put that, but that's a good idea.
It's normally the Brazilian colored bands, right?
We haven't put that out. But this is, I mean, we haven't put that out.
Like, would you say if you, it says you could plot the, like, say, like 95% confidence band of your expectation, and if your observation lies outside of it, can you say there's something wrong with the simulation, like simulated pseudo experiment?
Right. No, of course. The fact that they're so different. So your Brazilian band, I think, if I'm not, so this is your, so 95% and the 68% thing. So basically that band would be here, right?
But I thought those bands are like the rejection level at some
Yeah,
certain
you look at the
view.
p-value, yeah.
Right, but you're saying like because you ran so many different pseudo experiments, so that expected curve, there's like multiple expected curves, and then you just find a median, but if you could show the range, then
Yeah. So this is stuff we've done internally in Atlas, but we haven't put out that. It's full of lines basically. It's a good idea. Yeah, I mean we have them internally, but we have the paper usually has a very small subset of the studies we've done. But we've convinced ourselves that this gain is meaningful. But I mean it's a very legitimate question to ask. How is this so different? Yeah. But it's something we expected before we looked at the data because we've seen the histogram gain already. Okay. And then of course stat only results versus once we introduce nuisance parameters and profile over them, you expect the sensitivity to go down, and it does. But the nice thing is that the lower limit range, the effect of nuisance parameters is not that bad. Again, everything is consistent between the histogram and the NSBI method. Right. Okay. I think. So these are the fresh results that have come out this week. I want to finish on a comment on the future. I think this method is very exciting because not only it allows you to optimize over the full range of the theory phase space you want to study. And right now, when we do effective field theory studies, it has they have many operators and many parameters you want to measure. And traditionally in our analysis, we'll freeze all but one. And maybe look at so this is let's say a 2D space you want to scan, but instead you scan like a one line here, or maybe if you're very ambitious, you let two of them float. Because our methods are not very good at probing this 20-dimensional space, or for sure we don't optimize the analysis over this full 20-dimensional space. But now with NSBI, you can automatically optimize an analysis and really start to constrain 20 different parameters simultaneously. So I feel we're at the verge of doing very different kind of statistical analysis. Kind of like how I think in cosmology, MC was this moment that changed the way you were able to constrain parameters. I feel we're at a similar point here. So we'll see lots of SBI being used for EFT measurements. Cool, so to end, I hope I showed you that quantum interference breaks certain assumptions in our traditional statistical analysis tools, but NSBI allows us to recover that optimality. I showed you first in the pheno study why it's exciting, and then a method to actually implement it in Atlas, and then we actually applied it to data. Yeah, and I talked about wide-ranging applications in particle physics, astrophysics, cosmology, even beyond. This kind of idea has a lot of power. The weakness for this kind of method is the same as of a traditional analysis. You need to be very, very careful about systematic uncertainties, and also, of course, you need to have enough statistics to train your networks, because if they don't estimate the likelihood ratios properly, you're really in trouble. And so we have developed new diagnostic tools to convince ourselves that the network is doing well or to find problems, right? And when we use more and more powerful analysis tools, we also need to simultaneously build more powerful uncertainty quantification tools. We didn't have time to talk about all of that, but that's also a big focus of kind of work I do, so that we can really leverage these neural network-based methods. Thank you.
You.
So I had one question about, and I don't know, I think it's a few slides back, but you had these sort of learned relative likelihoods of a particular observable coming from, and you had the sum over different processes. And this was literally like a sum over diagrams.
Absolutely.
And I think what you said was that you trained, there was a neural network that was trained to compute those, but it was you had a different network trained to compute that for each different process. Now, of course, these different processes are not unrelated. Like if you go high enough order in perturbation theory, you see, if I have a diagram that says I take A and then A, B, and C happen, and I get, my output. This is strongly, the probability of that is strongly related to the individual probabilities of like these sub-processes. Is this something that we can use? Is this just not a useful thing because we don't go high enough order in perturbation theory to see this effect? Of like one diagram being like a sub-diagram of another that we've already learned to estimate?
Yeah, okay, this sounds very interesting. I want to understand exactly what you mean by sub-diagram. Can you give an example?
So I guess actually like a whole diagram wouldn't be a sub-diagram of another, but like, I mean literally in like the Feynman diagram sense, you could have, if you look at like some big diagram, you can snip off some parts of it and get new external legs, and now you have a sub-diagram. And if you go high enough order in perturbation theory, and again, I think this doesn't happen very often except fairly high order, so this may just not be like a useful idea.
No, it's very interesting. I haven't thought about that at all, but yeah, you're right. We're nowhere close to that order. So I definitely don't see like a Higgs diagram coming out of something else. I think, in fact, you're posing it as an opportunity. I think first of all it'll be a challenge, because then I can't break things apart, because like there'll secretly be a Higgs diagram even in this background diagram. Yeah, I'll have to do things differently there. So somehow I'll have to include the mu dependence here as well. And I think what you're suggesting would be a good way to handle that. Maybe I can, yeah, okay, so we'll have to sit down and do the math and see if we can, yeah. That's a very good idea.
You said you were using like your choice of the reference process.
Yeah.
Did you say you're using like the total
All the signal.
all the signal? Right.
It's a choice. I don't know if that's what I'll do in my next analysis, but you just want to make sure it's something that covers the whole phase space. You don't want zeros anywhere, and you don't want it to be very peaky. You want it to be nice and smooth.
So then, like you're learning that piece there, right? Like the ratio between some
So my
specific process.
reference, yeah, this is my for the example I showed. This is my reference.
So and that's the whole signal, or?
So I'm showing you only the gluon-gluon fusion. There's also electroweak diagrams that have the Higgs, so that goes in as well, and that's it. Yeah.
As a consumer, purely, has your analysis right now changed something? I mean, found something new, so that goes into particle data book?
So the confloat came out over the weekend. So this is fresh. To be very honest, so we got this dramatic improvement in the 4 lepton channel, but the Higgs width is constraints come from the 2L to nu, and we haven't applied this to that final state yet. So I think what I would like to do is in the next round apply to all final states, but particularly the 2L to nu, and then you will really have a significant shrinking in the constraint. That I mean that would definitely go into the
2026 edition.
I think Atlas does not allow me to comment on future things. It's being recorded, right? Yeah. So let's talk afterwards.
In the same vein, so I think it's slide 49. So the actual mu off shell that you plot, right? That's not the overall mu to 4 leptons, because I thought we had measured that to something like 6 or 7 plus sigma. I forget now what it is. So this is just purely shape information. How should I interpret mu off shell? What is that quantity?
No, this includes rate and shape information, but only I think I've said here 4 leptons, and then a big contribution comes from 2L to nu. So
is it? Am I right? So if mu equals 0 with the standard histogram method, looks like it's only excluded at, well, it's less than 95% confidence level. And I thought that just if you did, I mean, in the discovery papers alone, I thought it was already 4 sigma.
No, we haven't discovered the off-shell process yet.
Oh, off shell. Okay.
Oh yeah, that's right.
So
But we're close. If you combine everything, we're pretty close. So we're at 3 sigma and getting there.
yeah, but so that's the question. So what part of phase space are you looking at? I'm sorry, it's basic thing. So you're not looking at the 125 GeV.
Right. Oh, I'm sorry. I should have mentioned. Yeah. So the way you constrain the Higgs width is you take the off-shell Higgs, which is above 220 GeV, and the thing is, it's like the dependence on the Higgs width.
Above 220 of the combined invariant mass of
4 leptons. That's right. Yeah. And you need to combine the on-shell and off-shell measurement to get the Higgs width, which is a model-dependent-ish interpretation. But nonetheless, like if you can constrain, so the other stuff I haven't shown here is you can break this off-shell into the GGF off-shell and the VBF off-shell. And then if both of them agree, then they're kind of like alleviating this model-dependent interpretation. Yeah, which is why I would really like to do this in all the final states and all the production modes.
Okay, no more questions? Let's thank Aishik again.
Thank you very much.
So turn off the recording and then we can have some spicy questions. So if you